Hello and welcome to today's Learning Connection. Today you will learn how to integrate a virtual driving simulator into your development environment. More specifically, what will you learn today? We will learn what makes SUT integration in ZIL environments special, and how can you access simulation and sensor data with your system under task. Also, you want to learn how you can interface the vehicle and simulation from your SUT. And at the end, I will also show you how you can integrate the SUT API into your development environment. For today's agenda, we have the following points. First, I will explain what ASM and AURELION can deliver for your vehicle and environment simulation. Then I will go over to the XEL, which means X in the loop for hill and SIL, interfacing and synchronization topics. After that, we will go into more SUT-specific topics. We will explain how our SUT API enables you to interface the simulation to integrate your SUT with our simulation tools. After that, we dive into different integration examples. For example, with ROS, RTMaps, or a custom framework. And at the end, I will give you reach out to more advanced topics. So let's start with ASM and AURELION. ASM and AURELION are our vehicle and environment simulation tools. So let's start with ASM. ASM stands for Automotive Simulation Models. ASM are models for simulating vehicle models and traffic in real time or faster. We deliver them in an open Simulink models, which are platform independent and can run on MIL, SIL, HIL, and cloud platforms. You have access to all the components in the model and can make adaptations to your use case. Together with AURELION, our 3D environment simulation, we have also the sensor simulation integrated. AURELION provides sensor models for camera, radar, and LiDAR. Together with ASM in the co-simulation, AURELION receives position and orientation for all objects and performs the sensor simulation. Also for AURELION, we deliver open interfaces so that third-party models can integrate it into our AURELION simulation platform. And just as ASM, AURELION is also running on all platforms, on HIL, SIL, and cloud simulation. So with these two tools, ASM and AURELION, we have the simulation basis for your SUT. And now let's dive into the topics, how you can interface all the simulation capabilities of ASM and AURELION in your SUT. Let's do a bit theoretical background about XIL, interfacing, and synchronization. So the first thing is the distinction we want to do is open loop versus closed loop. So open loop, as it says, has no closed control loop. So as you can see in this presentation, you see that we have a simulator or a data replay, which sends sensor data to your system under test. But there's no way back. So there's no influence of the SUT on the simulation or the data replay. That's why we can use data replay in this use case. There are different use cases you can solve with these open loop simulations. For example, developing or validating a perception algorithm. On the other side, a closed loop simulation, as the name says, has a closed loop. Then we can send control signals, like for example a throttle value, from the SUT to the simulator. Now a data replay is not possible anymore. We need a live simulation, so the signals we receive are considered in a simulation. For example, use cases we can here do a full AD stack development, where not only perception is part, but also a controlling part, which is influencing the vehicle. So these two closed loop and open loop are available in both hill and sill simulations. But now let's distinguish hill and sill. When we take a first look in the hardware in the loop, so the hill simulation, where we use an SUT that is real hardware, we have a hill simulation. So what is important in a hill simulation? We're expecting results in real time, indicated here by the clocks on the top right corner of each of these boxes. So the simulator and the system under test are expecting results in real time. So there's no explicit coupling necessary, because the coupling is done by performing this real-time or considering this real-time task. Of course, then hill and SUT must run in real time, so they are required to have a very high performance. On the other side, in the software in the loop simulations, we don't have a real-time constraint. We are running independent of the real-world time. So what does this mean? We don't need to run in real time, but we need additional synchronization happening between the SUT and the simulator, because the sill simulator can only calculate if the SUT is done and the other way around. So with the sync interface, we are able to calculate independent of the real time, so we can calculate faster or slower, or even change the simulation time after each simulation step. Let's dive then in more detail. How can such a sync interface work? In general, it's a lock-in mechanism. So components of the simulation toolchain calculate after each other. So in our case, ASM, AURELION, and the SUT, we have 3 components. ASM is calculating, for example, with 1 millisecond. AURELION, for example, calculates a sensor with 40 milliseconds, and its SUT as well. So let's go through all the steps that make deterministic closed loop simulation happening. In the first step, ASM is calculating. And since ASM is calculating with 1 millisecond, it needs 40 time steps to calculate 1 new frame for AURELION. So it's performing all these 40 steps, and then AURELION is next in the tool chain to calculate. AURELION fetches the simulation data from ASM, which is essentially position and orientation for all objects, and performs the sensor simulation on this 3D environment currently. Since it's calculating one sensor, and the SUT is only calculating based on one sensor in this imagined scenario, AURELION does only need to calculate once and sends then the data to the SUT. So next is the SUT. It fetches the simulation data from AURELION. It also receives the simulation data from ASM and can now perform the task it's intended to do. For example, the perception and calculating a trajectory, for example, to control the vehicle. So after it's done with these information, it's sending back control data to ASM, for example, a throttle value or a steering angle. And then we are back at step 1, where ASM continues to calculate the vehicle simulation. So for all of these tasks and many more, we have one powerful API, the V-ESI API. It's able to do the synchronization task, perform the synchronization task, and enables the SUT to interface the simulation. So in general, it's the glue between ASM and AURELION to the SUT. So it's sending, for example, REST bus, open simulation interface, OSI, or sensor signals to the SUT. And it can send SUT data, for example, a desired acceleration or a steering angle, back to the ASM simulation. It's one central API because we want the API, the SUT API, to be as easy as possible for developers. And we wanted it to be simple and consistent. So with the V-ESI, we have one API with which you can interface everything you need in your SUT. So let's do a small distinction here. We have the V-ESI for software in the loop simulation, and we have also from dSPACE the ESI unit for hill simulation. So this distinction here is the ESI unit is used for hardware in the loop simulations. It's an FPGA board that is using the camera and sensor data and transforming the data in a customer-specific format for a full hardware in a loop simulation. On the other side, in the software in the loop simulation, we don't need an additional unit. We do use the V-ESI API or the interface. So there we have it is the flexible middleware we have for connecting all the system under tests. Okay, then let's have a more detailed look at what the V-ESI provides from ASM. So the first part of the simulation toolchain. For one thing, it's outputting the Open Simulation Interface, OSI, and in there the ground truth data. We go into more detail what this contains. Also, it contains REST bus data, which are the most used signals by our customers. So, for example, velocities, wheel speeds. But of course, the default signals we provide are not sufficient for all use cases. So we also provide custom data, which means customer-specific information from the model, which can be anything that is available in the ASM model or extensions to it. So let's go into the Open Simulation Interface. The Open Simulation Interface is an ASM standard, which provides 3D environment information for the vehicle, so the ground truth area. You can see in here in this visualization on the right side our 3D visualization, and on the left side the Open Simulation Interface data. In this case, visualized with control disk. You can see the bounding boxes for the vehicles with the correct position, orientation, and dimensions, as well as lane boundaries, lane topology information, with color information, and also information, for example, about guardrails and many more. With the Open Simulation Interface, you can, for example, skip the perception task of your SUT and go directly into the control part. Or, for example, you can do a validation of your perception using this ground truth information. So you can check if the bounding boxes your SUT detected are close to the bounding boxes that we deliver as ground truth information. So we deliver all the information in the Open Simulation Interface about moving objects, all the information in there, like for example, road information on which lane are objects driving, their light states, also information for the stationary objects with all the position, also in the lane topology, the lanes themselves, so which lanes are connected to each other, where are junctions, where's the center line, and so on. And the corresponding lane boundaries that limit the area of the lanes. And additionally, also the semantic information for all the stationary objects, or traffic signs, for example, traffic lights and road markings. Can in there have information about the traffic sign types and also even text information that is displayed on traffic signs. This has been the Open Simulation Interface, or the data we provide with the Open Simulation Interface. We also have an output for custom data, so data that can be customer specific and can be anything that is in the model. So in there, we are using Simulink buses. So on the first step, you have a Simulink bus in the ASM model. For example, here you can see the ASM bus with the electrical system, the driver assistance, environment, and so on. And what you want to receive in the SUT are all these informations programmatically. So you don't want to integrate it into the Simulink model. You want to have the data directly in your SUT. And that's why we are converting this ASM bus, or it can be any bus at all, with also extensions to the ASM bus, into a C struct. So in here you can see, for example, this C struct which is the ASM bus with all these components, and they have buses within them or structs within them. And with this C struct, you are getting all the custom data from the model. So let's show what this looks like in the tooling. So let's take a look in Simulink. We are now in the Simulink model of ASM traffic. In here, on the left, you can see all the ASM bus signals that are sent to the V-ESI via custom data. You can see in the Simulink bus all the signals available within the ASM bus. For example, in vehicle dynamics, we have a vehicle movement and all the vehicle velocities, for example, V total vehicle. With all these information, we want to feed our SUT. So after generating an header file from this ASM bus, which is shown here, we can access all the signals in our SUT. You can see in the header file all the components we have seen before, and in our SUT we can easily access all of these signals. For example, here I want to print out the velocity of our vehicle. So I can go into our custom data, which I'm receiving here in our SUT here, go into our vehicle dynamics. Can see with IntelliSense, can see that it's easy to access all the signals available in the SUT. Can see we have now the same signal I have selected in Simulink in our SUT and can run the simulation with this component included. So next, let's have a look at the V-ESI data from AURELION. So in AURELION, we have a camera simulation, a LiDAR simulation, and a radar simulation available. And here as well, we have the camera image available in the V-ESI, the LiDAR point cloud, and for radar, we have the paths, the detections, and also the ADC samples. Yeah, all these data can be accessed directly from the V-ESI and also with additional information, not only sensor-specific information, like ground truth information. So segmentation for camera, or also object ID information in the LiDAR point cloud. So let's again take a look at what this looks like in the API. We have here AURELION running on my machine. You can see the vehicle in the overview and also the camera sensor that is simulated currently. The sensor is placed in the front windshield of this car. Now we want to access this sensor data in our SUT. We can do that with the SUT API V-ESI. Let's take a look at the code from the SUT. In this SUT code, you can see everything is already written out. You can see in this, after this comment, read sensor data, the different steps necessary to read the sensor data. We have a sensor data written into the atomic sensor information class. And we can request the sensor data via API and write it into our sensor data. And at the end, I have my own function, visualize sensor data, which takes the sensor data and creates a new window to show the results. It's only an input, the input is only shown. Nothing special is happening here. Of course, with the same API, we can also access other sensor types, like for example, a LiDAR sensor. If we would request a LiDAR sensor data, let's take a look at what this data would look like. We would use the same class, atomic sensor information, but receive LiDAR data, which you can see here. It's generally a list of LiDAR points, each consisting of different information useful for a LiDAR simulation. So for example, the normal of the LiDAR point, the azimuth, elevation, distance, and many more. We are also providing ground truth information here. For example, the object ID, the array ID, or the material ID. But for now, we will stick to the camera sensor and visualize it. From the last step, we added also the velocity. So the velocity and the camera image should now be visible to us. Let's take a look. First, of course, I have to build this new SUT. For me, my SUT is only an exe file, an executable, which I can run here by running main. Now we can see we are printing out the velocity of the car, and opened on my other screen, can see now the camera image visualized in a new window. So both of these information, the custom data and the camera data, are available to me. Next, let's take a look at the way back. We have seen how you can access the simulation and sensor data in your SUT, but now you want to control the vehicle. So your SUT is sending control signals to the ASM simulation. For this, we have a similar approach to the custom data on the other way. So we are sending an C struct, which contains all the signals we want to send to the simulation, to the Simulink model. So we have a C struct and the corresponding Simulink bus in Simulink. In here, we can have all the signals our SUT wants to control for the vehicle. This can be, for example, the steering angle, enabling the steering axis. So for example, hands-off, hands-on scenarios with the simulated driver. Or, for example, brake lights. With this C-struct sending to the ASM model, we have a generic approach. So you can have other signals than the predefined signals we provide and extend this list by anything you need for your use case. Secondly, we have this controlling of the simulation time. So we are currently in a state where ASM is paused and the SUT is running. But we want our SUT to be paused and ASM running. So by running this command you see on the right here, so api.increase simulation time, we can continue the ASM simulation, in this case by 40 milliseconds. So with this interface, we ensure with the V-ESI API that we have a deterministic simulation. But still, the user or developer has the full access to the simulation time and can control it desired to the use case. So let's take a look what these API calls look like in the tooling. In here, I have my result data from the V-ESI. So the control signals I want to send back from the SUT to the simulation. In this header file, all the signals I want to send back to the model are defined. You can see in here, we have, for example, enable acceleration pedal and the position, or a gear we want to select. With this header file, we generate a signal bus in the Simulink model we want to send back to the Simulink model. You can see here the same signals we have defined before in the Simulink bus. Now, of course, we want to define these signals and send them back to the model. Can do that in our SUT code we have discovered before with V-ESI result data. So we define this struct, and now we can assign values. For example, we want to enable, let's say, we want to request an acceleration from the vehicle. Let's say we want to have acceleration of 5 meters per second squared. So with these two values, we are sending back a signal to the model and want to have an acceleration of 5 meters per second squared. You can see we send this with this api.send control data command to our simulation. Also, we we want to increase the simulation time now, because we are running now in a closed loop simulation. So with increased simulation time and the desired factor of, let's say, 20 milliseconds, we have an SUT written that's running a closed loop, sending the control data and increasing the simulation time from within the SUT. But since this example is not very interesting, let's have a look at a more detailed example at a later point. So you have seen what the access to the simulation or controlling the vehicle looks like. Next, let's look at what supported platforms we have for the V-ESI API. We have Windows and Linux available in the product. And other examples are also possible. For example, Linux and ARM or QNX. Just get in contact with us. This has been the theory. So now we want to take a look at what integration examples look like. So let's start with the generic approach. The most generic approach is to have a custom solution. So the custom solution is shown here. We have the V-ESI API, C++, C library with its DLL, header file and library. This is the bare minimum for the V-ESI library. And with this API, any custom solution can be built upon. For example, the ROS and RTMaps solution we show after this are the very same thing, just a custom solution using the V-ESI API. And since we are using a C library and a header file, which is a common standard for APIs, we can have bindings for nearly all programming languages. So let's start with a simple example I have on my machine, which is built directly with the V-ESI API as an exe file. We have now here our AURELION camera, which is again placed behind the windshield of the vehicle. And the task of our SUT is to do a perception on this environment, detect the currently driven lane, and to try to keep in this lane. So active lane keeping assistant. This SUT is now integrated in a Visual Studio project, which you can see here. And in here, we have the SUT just as defined as before. So we are requesting sensor data from the camera. We are detecting lines, so that we see the lines of our lane. And we request custom data because this SUT is also trying to keep a defined velocity. And at the end, we send control data back to the simulation, so our desired acceleration and steering angle, and increasing the simulation time for the deterministic closed loop simulation. So let's run this SUT and see what it looks like. The SUT has opened up now 3 windows, which help us to debug what the SUT sees. So this is the full SUT output. Here is the filtered one. And here we have the basic SUT perception. On the top left, you see the environment filtered by color. On the right, filtered by area, so the bottom area here. And at the end, we have this result. So the full detection running on this environment. You can see in green the lane we are detecting, we're driving on, and on with red, the boundaries. And on the top, we can also see our current velocity, the set steering output, so what our SUT sets as a steering angle. And on the top, we see the current running control, if we are steering to the right or to the left. So let's see if our SUT manages to steer in this road. You can now see our SUT is succeeding. For one thing, it's reached its desired velocity of 60 kilometers per hour. And also can see by the camera image, the vehicle is still in the lane, even though there has been a curve. So our SUT is able, based on the camera image, to steer the vehicle. And our ASM and AURELION simulation provide the environment to test this SUT and develop it further. Okay, this was the custom solution I have shown. Now let's dive into more sophisticated frameworks. The first one we could use is the Robot Operating System, ROS. ROS is an open source framework for developing robots. It provides a large ecosystem of algorithms, sensors, and control interfaces. In here, you can also see visualization parts of ROS that help you develop these algorithms. The robot operating system is widely used by ADAS AD customers, so we want to support ROS as well. So on my machine, I have a ROS example. Let's have a look what it looks in the tooling. We have once again a running simulation in AURELION, as you can see in this camera image from the AURELION. Now we want to take a look at what the coupling with ROS looks like. For this, I have already prepared 3 windows. Let's start ROS Core. For the ROS environment, and also AVIS for the sensor visualization. You can see I'm running here on my Windows machine, but I'm using Windows subsystem for Linux, so I can run ROS within Windows. We have now open AVIS for visualization, and as a last step, I will start the camera node. So what does this ROS node do? It takes the camera image from AURELION with the V-ESI API and sends it into the top ROS. So let's start this node and see if we can receive the camera image and visualize it in AVIS. So let's see if we can find a new topic. And as we can see, sensor image 1_1, that's our camera image. And here we can see the simulated image from AURELION available in ROS in the visualization AVIS. You can see we have accessed it with its IP and port from our Windows host system, which is simulating the environment. Similarly, we can also visualize LiDAR and radar data or distribute, let's say, ASM data, for example, to make transformations available. Okay, this has been the ROS framework. Another framework we wanted to support is RTMaps. RTMaps is real-time multi-sensor applications. And it's a visual framework for developing multi-sensor applications, as the name suggests. So it's widely as well used for ADAS AD and robotics, and essentially has many similar components to ROS. And it has a visual framework, so you can have a look at your nodes and what the components look like connected to each other. It can help in many different tasks, like, for example, perception, localization, mapping, prediction, planning, or control. And RTMaps is available as a development environment and also as a runtime, so headless, only with the code running. And it also provides a big ecosystem for algorithms and sensor interfaces. And in my machine, I have an RTMaps example as well. So let's have a look what the tooling looks like in RTMaps and how we can interface the sensor and simulation data in there. I have again a running simulation in AURELION and ASM, as you can see here in AURELION. But the simulation is currently in a locked state because it's waiting for instructions from the SUT. As SUT, or as a SUT framework, I'm using here RTMaps. And you can see the prepared diagram. The diagram consists of two systems. For one thing, we have this request sensor data component, which is requesting the camera data from AURELION and visualizing it within our RTMaps image viewer. On the other side, I have a send control data component. This is increasing the simulation time and sending the control signals from RTMaps to ASM. As you can see, I have two sliders here. With one slider, I will be able to control the acceleration of the vehicle. As a second slider, I'm controlling the steering wheel of the car. So in principle, with this RTMaps diagram, I should be able to drive the vehicle based on the camera image received here in RTMaps. So let's see if this works. I'm starting the SUT, and as you can see, the simulation starts to run. You can see the fellows disappearing and my controls here on the left. So let's start accelerating a bit. So for now, I would say 2.5 meters per second squared should be enough. As you can see, the velocity is increasing, and I have also a slight angle to the left. So let's try to drive a bit more to the right, maybe a bit too much. Yeah, and as you can see, it's quite hard to drive as a human with only two sliders. An algorithm, of course, would be doing a better job than I'm doing here. So let's stop the simulation here. Yeah, and as you have seen, I'm able to see the signals and the camera image here in RTMaps and control the vehicle. Then in reality, of course, you would replace these components with the algorithm parts for your SUT. Yeah, these have been the implementation examples. So a custom solution, integration into the robot operating system, and RTMaps. So let's go into more deeper topics. The first one is multi-SUT and AURELION systems. So if we have a very demanding sensor set in our simulations, like many cameras, many LiDARs, and so on, we have to distribute our simulation. So with our toolchain, we support this, so we can have multiple AURELION instances per ASM simulation. And all of them are performing sensor simulation, which are sent to different SUTs. So in this example, we have AURELION instance 1 and 2, which could be, for example, each 4 cameras, which are sent to a perception SUT, specialized for camera perception. And then a third AURELION instance, for example, calculating LiDAR data to a LiDAR perception SUT. And also these architectures are possible, so we can have different AURELION instances sending to different SUTs. Then those two SUTs send their data to a control SUT that's performing the control calculation, and which sending this data back to ASM. So a complex system like this is also possible. You can scale the number of AURELION instances. You can have the SUT or the API distributed across many SUTs and have even different update rates for each of them. All of this is possible as well. So with this API we have, such use cases can be delivered. Another advanced topic that I wanted to show is the validation with the V-ESI in hill applications. For now, we took a look at SIL applications, but the V-ESI can be used for hill applications as well. So let's take a look what is visible here. We have ASM running on Scalexio and sending the simulation data to AURELION. But also with the OZGT, so the Open Simulation Interface data, we are sending it to a validation component, also running parallel to the simulation. And at the end, our SUT, which is receiving the AURELION data, is sending its perception results. So for example, the bounding boxes detected by the camera. And with the V-ESI, there's one API with which you can, in the validation component, validate your perception in this hill simulation. So the SUT is not used to send signals back to ASM or to control the simulation time, but rather to validate the perception. So this enables an easy debugging of real-world data with all the important data points. So you can have sensor signals, you have the ground truth result data, you have the perception result, and you can have KPIs. This has been all for today's session. You have seen how you have powerful and full access to the simulation and sensor data with the V-ESI, our powerful and open API. Thank you for listening.
Hello and a warm welcome also from my side to this learning connection. So this is Christopher Wiegand speaking, and I will moderate this Q&A. So we have received a few questions within the chat and also at the registration. So there are really some very interesting questions here. It seems most of them are very technical. The first question, is there a possibility to feed the simulation environment with an HD map of real-world location? Example, given HD map tile of a city.
Yeah, the short answer is yes, there are possibilities. And the long answer is there are different ones. We have, for one thing, open standards, or we support open standards with our tooling, like for example, TomTom, OSM, or OpenDrive, with which you can import HD maps. But also on the other side, we are working together with partners that deliver HD maps, like for example, 3D mapping solutions. And with these partners, we can have great results in importing 3D environments from HD maps, so in the simulation and also in the 3D environment.
Sounds good. Thanks, Thomas. Next question in the chat. So why is the system under test in software in the loop taking 40 milliseconds?
In this case, it's an imagined scenario. It must not take 40 milliseconds, can be any time you want. In this case, we had a camera, for example, that's taking 40 milliseconds to calculate a new image or to deliver a new image. So for each frame the camera delivers, the SUT is calculating, and then again waiting 40 milliseconds. So that's why there was 40 milliseconds. Of course, if the SUT needs to recalculate every 10 milliseconds or any other different time, that's also possible. So in this case, it was only an imagined scenario where the camera was taking so long.
Thank you. So the next one is, we would like to use the V-ESI API for object list sensors in ASM as well. Are they also accessible with the API?
Yeah, that's a good question. We have, so just a bit explanation around it. We have of course the AURELION sensors, which do the physical sensor simulation, but we also have object list sensors, how we are calling them. They do not operate on a physical level, but rather output object lists, which also help develop functions. And they are also available. And they are available at the custom data. So the custom data we send from ASM, in the signal bus, you have access to all the object list sensors from ASM as well.
Okay, thank you. So here's a question which is related to our driving simulator connections or interfaces. So do the ASM models support static or dynamic simulators, such as Cruden driving simulators for steering and brakes and so on?
Yeah, maybe for that I can show a quick slide. And yeah, also the answer here is yes. So we support also driving simulators here, for example, the Cruden driving simulator. In this case, for example, you see it's a dynamic one because the cabin of the car is also moving. And in the case of a driving simulator, we can also perform a coupling with the simulation, either hill or even hill. So you have the signals from the driving simulator sent back to ASM, and the signals from ASM to the simulator to move the cabin of the car. It's kind of similar to the RTMaps example I have shown, but rather than sliders on my screen, you are using the steering wheel of the car and having an exact steering. Another example we have for driving simulators is, for example, a static one with M Dynamics. And here as well, we have ASM Vehicle Dynamics coupled, and also using AURELION, as you can see on the top here, for the 3D visualization. So for the photorealistic simulation, to see where you're driving, we can use AURELION as well.
Okay, then we have another one. Thanks, another one. This is a thanks to you, Thomas, I guess. In SIL and ASM is running at 1 millisecond, but it is then paused for 80 milliseconds, 40 milliseconds for AURELION, and 40 milliseconds for SUT. Is it the same of having ASM running in 80 milliseconds?
I hope I catch the question right. So if the SUT is running with a lower frequency than ASM, then you will not have running with the wider step width, but keep ASM running with 1 milliseconds, because that's results in a higher accuracy in the simulation. So ASM will then do 80 steps and then send out the result to AURELION, and then the control loop goes further. So for highest, to keep the high accuracy of ASM will not run at a higher frequency, a lower frequency. It keeps this high frequency of 1 kilohertz.
Maybe one additional comment to the ASM step size. And ASM models are real-time models, and they are developed to run in real time. And therefore, this millisecond is important to guarantee stable results. So with respect to numerical stability and things like that. So let's go maybe to the next question. So in a closed loop HIL environment using several LiDAR sensors and cameras, is this system still capable of real-time simulations? Where are the limits?
Yeah, the short answer is yes. So our goal with AURELION is to have an hill capable 3D sensor simulation. So we deliver models that are real-time capable. Of course, it depends then on the boundary conditions. I have shown on one slide the distributed system where you have multiple AURELION systems distributed AURELION instances on many machines running. And with this approach, we can scale to have a bigger sensor set simulated. So we could even have LiDAR sensors that are too demanding for one GPU distributed across many GPUs, and then you will then again reach real-timeness in the simulation. But of course, it depends on the conditions and everything, how many LiDAR points, how many LiDARs, which GPUs are used. But generally, we have a scalable approach and can reach real time.
Then we have a rather technical question. So you have shown that it is possible to generate the header files for custom data from the Simulink bus. Is it also possible the other way around? So to generate the Simulink bus for custom data from a given header file?
Yeah, maybe I can share the screen again and jump to the slide back. and show a bit more. So it's about these slides. So if it's also possible to define, I understand, this header file and generate a Simulink bus. And that's also possible. So you can define a Simulink header and then generate a signal bus, which is then available in the Simulink model. And of course, you then have to connect the signals from the model to have proper signals also available in the header, but that approach is also possible. So the other way around. First the header, then the bus, and then everything is available in the SUT.
Sounds good. And let's go to the next one. So I'm able to increase the simulation time from the SUT. How do I know by which increment I have to increase the simulation time?
Yeah, that's a good question also. There is a pitfall. You can set values that don't make sense. You of course have to look at your whole simulation and see what your sensor is calculating at which refresh rate. And then you set this value as an update rate. Of course, ASM also needs to send at the same rate, but then you have a functional chain in the end and don't run into a deadlock. So consider the bonds you're using, and then you can set a value that makes sense.
So this is one also. So how many of the presented technologies, ASM, AURELION, virtual ESI, ESI unit, are open source or can be used, integrated in custom applications, if any, and how many are dSPACE proprietary?
Yeah, generally everything can be integrated in custom applications. So we always provide open tools. Additionally, like for example, in ASM, we are making also the whole model structure available to the customer. So you can take a look at the internals of ASM and see how things work. Or for example, in a V-ESI, you have access to the API. The whole header files are open to the user, and he can take a look at how he can get data, how he can send data, and how things work. So all these things are meant to be used in custom applications. Some things, of course, are proprietary, like internals of the sensor simulation. They are not fully open, but the interfaces all are. And we always try to provide the most open interfaces. For example, in AURELION, we have for our sensors a post-processing where you can even run on the GPU, things that run on the GPU to post-process sensor data. So yeah, keeping us open for custom applications.
Thanks a lot, Thomas. So maybe this one, how the HIL setup will be if we have an external simulation environment such as Scala or Unreal Engine.
Yeah, that's a interesting question. It depends what things are simulated by ASM, AURELION, and which ones by Scala and Unreal Engine. But generally, if you use our components, we can openly provide the signals from the simulation also in the HIL setup, so that you have access to things we deliver. Of course, then in Scala or Unreal Engine or other custom solutions, it depends what data they output. There will not be a solution from the beginning, but it will be possible, of course, to build up a custom solution for that and have, for example, this validation part running with Scala or the Unreal Engine.
Could you maybe give some comments about the synchronization with respect to the road? Because I assume, considering the vehicle dynamics and 3D environment, there is something to do. Am I right? Yeah,
that's correct. So it will not be a straight solution. It will not work from beginning, not plug and play, let's say. There needs there are some adaptations at least necessary. But yeah, it's a bit of out of scope maybe for a few minutes we have here. So
this is interesting, I think. More and more question. Good to see. So do you have or plan a cloud solution, or these tools are just for desktop and server context?
yeah, that's a good question. We have a cloud solution. It's a new tool by dSPACE called dSPACE Simfera. With Simfera, we have a cloud solution available in which you can scalable run simulations, also with the V-ESI API. So the same API you use for the local use case, you can also use in the cloud. So we have something available there. Maybe look into dSPACE Simfera. I think that might be the choice for you.
So now I guess more or less everything is answered. Give me 1 second. Maybe this is not tackled so far. So in order to evaluation, can we export ASM simulated vehicle data parameters? If yes, then in which file format?
Yeah, the ASM vehicle parameters can all be exported and are open to the user. So they are based as XML files and yeah, can be read with any text file reader, let's say, or be evaluated programmatically.
I'm not sure. Okay, there's one. I'm sorry. With regard to the example where the vehicle was keeping the center of the line, what is the source of the information about the road infrastructure, lane width, etc.?
In that case, it was only based on the camera image. So the only input we took in the SUT was the camera image. Of course, that was an algorithm developed, not intended for production use in a real car, and very highly specialized for the scenario we run it in. So it took it for granted that we have a specific lane width. Of course, we have also the lane width in the simulation environment available. So if the SUT then needs this information, those would be available as well. But in our case, we did not need it.
Sounds good. So we have 2 additional LiDAR questions, quite interesting ones. So can the data from the LiDAR sensor be evaluated by the pulse width full waveform? Is multi-echo supported by your LiDAR sensors?
Yeah, those are quite technical questions. Multi-echo is at least supported by the LiDAR sensors. We also output a lot of raw data with the LiDAR sensor, more than I have seen, or maybe more than you have seen here in my presentation in the header file. They can be, for example, accessed from post-processing. But maybe get in contact with us if you have more detailed questions. We set you up with more appropriate answers so that you get more details. Yeah.
Yes. So I think we will get in touch with you with that regard. I think most of them is already covered. So that's all, I guess. So we are through with all these questions. Thanks a lot. And thanks to the audience.
Excellent. Thank you so much. Thank you, gentlemen. There were a lot of questions and I think they were all answered. If it wasn't answered, then what we'll do is we will get back to you because we've got it, because you typed it in, we've got it. Then we can go ahead and we can email you after the event. So thanks again, everybody. Thank you for being here at the Learning Connection. This session was recorded. So if you want to see more, then what you can do is you can go ahead and you can go to our website, and that's dspaceinc.com under the Learning Center. And as you exit this webinar, a short survey will automatically open. So we hope that you'll leave us a little bit of feedback on that survey. Have a wonderful day, and thank you very much from the dSPACE Learning Connection.